welcome to this college algebra video on graphs of basic power functions and polynomial functions. Before we get started, let's review what we know about zeros of a polynomial. So take just a second to try to find the zeros of each of these polynomial functions. You can pause the video and try it yourself, and then rejoin when you've tried these problems. All right, now that you've had a chance to try these problems for yourself, let's check the solutions. For the function f of x, our first solution that we see is x equals -3. The factor of x plus 3 gives us that first solution. Now this factor does happen twice, so we could say that this solution has multiplicity 2. The second solution comes from the factor x minus 8, and that solution would be x equals +8. That factor only happens once, so that solution only happens once. We would say it has multiplicity 1. And finally, the factor x minus 12 gives us a solution of x equals +12, and that solution occurs only once, has multiplicity 1. Let's go down to g of x. The function g of x is not already factored, so I am going to the function g of x is not in a factored form, so I'm going to first use a graphing calculator to see what solutions might show up just on a graph. Remember that the zeros of this polynomial are the same as the x-intercepts that I would see on the graph. So I'm going to start with a zoom 6. From the graph, I can see one solution, and as it continues to graph, there's 2 and 3. So I'm seeing 3 solutions. According to the fundamental theorem of algebra, a degree 3 polynomial should only have 3 solutions. So it looks like I can see all of them on this screen. Let's try and find out what these solutions are. The first solution on the left looks like it could be at an integer value, -5. Let's check and see if -5 gives us a 0 of the function. It does. And the next one looks like it could be at +5. Again, I'm using trace. I'll find out if it does produce a 0. Yes. At 5, the y value is 0. And the final one looks like it might possibly be at x equals 6. And let's check that third solution. If we're still tracing and hit x equals 6, yes, the y value there is 0. So this time from the graph, we were able to find the 3 zeros of this polynomial. X equals -5, x equals +5, and x equals +6. So we'll see that the zeros of a polynomial are important aspects of the graph. However, that's not the only thing about a polynomial graph that's important to us. So let's take just a minute and we'll use Desmos to explore some other features of what we call power functions and polynomial functions. We're starting here with a graph of a function where the coefficient is 1 and the power is 1. So this is 1x to the first power, or just the function y equals x. We've got a familiar straight line here, and as we know, the coefficient that's in front of the x basically means the slope of the line. As that coefficient gets bigger, that slope gets steeper. As the coefficient gets smaller, the slope gets less steep. We could get down to even a slope of 0, which would be a horizontal line. And as that coefficient turns negative, we now have a line with a negative slope. Well, let's change the power of x to n equals 2. This is the function y equals x squared. We've already studied parabolas pretty extensively. We know that we should have a parabola shape for a quadratic. And again, as the coefficient in front of that x squared gets bigger, the parabola gets steeper. As the coefficient gets smaller, the parabola gets less steep and it can actually sort of be squashed down. If we have a coefficient of 0, then this graph is completely flattened out. And the coefficient in front of x squared, if it's negative, now we have a parabola that opens downward instead of upward. Let's change that power again to a third power. And this may or may not be familiar to you, but if we look at an x cubed graph, here's the basic shape we have. Notice just kind of like the straight line, it starts down and to the left and goes through the origin and ends by going off up to the right. Now, as the coefficient in front of x cubed gets bigger and bigger, that graph will stretch out vertically. If the coefficient gets smaller or closer to 0, then that cubic function, that swoosh that's kind of happening, is going to flatten out a little bit. At 0, we'll have a completely flat graph. And if the coefficient turns negative, now we've got a swoosh that starts up and high to the left and finishes by continuing off down and to the right. So we can have a positive x cubed graph or a negative x cubed graph. Let's try a graph with a power of 4. So we've seen x squared, x cubed. What about x to the 4th? Here's what the graph of x to the 4th looks like. It looks very close to what we saw when we saw x squared. It's still sort of a parabola shape, but this isn't exactly called a parabola. What you'll notice is that the inside, the part between -1 and 1, is kind of squashed down a little bit closer, but still has this basic U shape. And as the coefficient gets bigger, this gets steeper. As the coefficient gets closer to 0, this thing flattens out. And if we put the coefficient negative, now we have a U shape opening downward. So the x to the 4th graph has a lot in common with the x squared graph. Let's take a look at an x to the 5th graph. This graph looks very similar to our x cubed graph. It starts low and to the left and continues up and up and up through the origin, kind of makes this swoosh, and then continues up and to the right. As the coefficient gets bigger, it stretches. If the coefficient gets smaller, it's squashed down, and a negative coefficient is going to cause it to go in the other direction, starting high, going through the origin, and ending low. So x to the 5th seems very similar to x cubed. If you had to guess, what do you suppose x to the 6th will look like? Well, if you guess that it's going to be the U shape, you're correct. An x to the 6th graph is a U shape like an x squared. An x to the 7th graph is the swoosh shape, just like x cubed. X to the 8th, back to the U shape. X to the 9th, back to the swoosh shape. So even powers of x all seem to have this U shape. Odd powers of x all seem to have this swoosh shape. Now let's consider this x to the 7th graph, and let's see what happens if we add another power of x onto this to create now a polynomial, not just a power function, but this has more than one term, and so we can call it a polynomial. And let's add an x to the 6th term. Let's see if now it is going to follow the pattern for an even power or an odd power. Well, if we add x to the 6th, we can still see the basic shape for an odd power. X to the 6th was not enough. Maybe we just didn't add enough even powered terms here. Let's add an x to the 4th power. Nope, still the basic swoosh shape. We do have, looks like an attempt to make a U shape, but overall that x to the 7th power is still winning. Let's add an x squared term. Still not a U shape. The x to the 7th power seems to be dominating what the basic shape of the graph is. Let's now consider this x to the 8th power function. And let's try to see if adding some odd powers of x could finally convince this thing to change its shape from a U into the swoosh that we've seen for odd powers. So let's add x to the 7th power. Still basically a U shape. What if we add x to the 5th power? Still basically a U shape. Add an x to the 3rd power. still basically a U shape. It almost looks as though if we looked at it from the right and towards the middle, it looks like this thing is sort of looking like it's trying to make a swoosh shape, but eventually that U shape dominates this function. And the term that determines which shape it is the leading term. That highest power of x that you see is going to determine the basic overall shape of the graph. Now, what these other terms will do is they might provide some wiggles within the graph. So let's summarize what we've learned. For any polynomial of odd degree, that is ax to the third power, ax to the fifth power, ax to the seventh power, any polynomial of odd degree, when the leading coefficient is greater than 0, we're going to see a basic shape that looks like this. If the leading coefficient, that a, is a negative number, we're going to see a shape that looks basically like this. Now, the rest of the terms of the polynomial, if they are even powers of x or odd powers of x or however many terms you add on here, they're not going to change the basic end behavior of the graph. That's what we call this, what it does on the outsides. All those terms can do is make the graph wiggle around a little bit in the middle, but the basic end behaviors of these graphs are going to stay the same. Now, if you have a polynomial of even degree, that is, you're starting out with ax squared, ax to the fourth, ax to the sixth, any even power of x as your leading term. Well, when the coefficient is greater than 0, an a value greater than 0, you'll see a U shape where the U opens upward. If the coefficient is less than 0, that is a negative value for a, we'll see a basic U shape that opens downward. And again, the rest of the terms cannot affect the basic outside behavior of the graph, only affects how much it wiggles around inside. So if you're watching this video on a computer screen or maybe watching it on your phone, now might be a great time to get up and take a little stretch. And while you're stretching, you can actually be reviewing these concepts we've just talked about here. Let me show you a couple of dance moves here that you can do to get yourself limbered up and practice basic shapes of functions at the same time. So you could practice the y equals x function. You could practice the y equals x squared function. You could practice the y equals x cubed function. You could do the negatives of all these functions. Y equals negative x, or y equals negative x squared. Now, what would that look like? I suppose both arms down. Or y equals negative x cubed. Have the left arm down and the right arm up. So have a little fun with these things and enjoy learning the basic graphs of power functions. Let's also recall some of the basic graph transformations that can happen. And we've seen all these transformations specifically with quadratics, but they can apply to any kind of power function. So we can shift a graph up or down or to the right or to the left by adding a number inside the function or outside the function. We can stretch a graph or squash a graph by multiplying the function times some constant. We can reflect any of these graphs over the x-axis by multiplying the whole function times -1. Remember, any vertical transformation happens by adding or multiplying the constant to the whole function or kind of outside the function. Any horizontal transformation happens by adding the constant or multiplying the constant to every x in the function. So we sort of say that happens inside the function. Now let's use all these concepts to get a basic outline of what these graphs would look like. Here are a couple of examples. Negative quantity x minus 7 to the third power. So to graph f of x, first of all, we know that this is a cubic function, and a cubic function has a basic swoosh shape, either like this or like this. So when we see this negative sign in front of the quantity x minus 7 cubed, we know that this graph is going to start high and end low. This is basically the x cubed graph reflected. Now, the last detail we look at here is the fact that we are subtracting 7 inside the function. So what does that do? It moves this function 7 units to the right. So at x equals 7, that's where the graph is going to kind of cross through the x-axis. And our graph, again, will start high and end low. So this is an approximate graph of negative quantity x minus 7 to the third power. Let's focus on g of x. It's quantity x plus 5 to the fourth power plus 2. Well, an x to the fourth power graph, it's either a U shape that opens upward or a U shape that opens downward. Well, when I look in front of that quantity to the fourth power, I don't see any negative sign here. It's not being reflected upside down, so it's a U shape that opens upward. The plus 5 inside this parentheses is going to shift this graph 5 units to the left. Plus 2 at the end of the quantity to the fourth is going to shift this graph 2 units up. The vertex is going to be at coordinates negative 5, positive 2, and we'll have a U shape from there. So we've seen how important it is to know that leading term of a polynomial, that highest power of x and the coefficient in front of it, because it tells us what the graph is going to look like kind of on a big scale on the outsides of the function. But let's return to some of the things that we saw in the warm-up problems that we did at the beginning of this lesson. And here we're going to see how multiplicity of roots can tell us something about the shape of this function as well. So it turns out that from a factored form of a polynomial, we can tell not just where the graph crosses the x-axis, but also how the graph crosses the x-axis. So as a reminder, when we have a factor of x minus a in our polynomial, the value that makes that factor equal 0, which would be x equals a, is a 0 of the function. It is also an x-intercept of the function. When we go back and look at our two warm-up problems, we can see in g of x, which I've now written in its factored form, x plus 5, x minus 5, x minus 6, each of those factors shows me one of the x-intercepts of that function. That also means that the zeros of the polynomial f of x, negative 3, 8, and 12, those should also show up as x-intercepts on a graph. And let's take a look at that. Here's the graph of f of x, and we can see that one of the x-intercepts is indeed at negative 3, another x-intercept is at positive 8, and another x-intercept is at positive 12. But there's something in particular I want to point out about this 0 here at x equals negative 3. Let's zoom in on that x-intercept a bit. What we notice here is that this particular x-intercept is different from all the others that we've seen. Instead of the graph crossing through the x-axis, this graph comes up here and touches the x-axis in exactly one point and then continues back down. And you may notice that the only difference between the factor that gives us x equals negative 3 and the factors that give us x equals 8 and x equals 12 is this power of x plus 3. The fact that x equals negative 3 has multiplicity 2 and the others have multiplicity 1. And here's the concept that illustrates. For odd powered factors, or zeros that happen with odd multiplicity, the graph will cross right through the x-axis. It'll go from negatives to the positives or from the positives to the negatives. But for even powered factors, those zeros that have even multiplicity, 2, 4, 6, or so on, what we say is that the graph kisses the x-axis. It touches the x-axis and then turns back. It does not make it all the way through from the negative to the positive. If it's negative, it just touches the x-axis and turns around and stays negative. If it's positive, the graph touches the x-axis and turns around and continues to be positive. Let's look at this example where we can use some of these concepts to analyze this function. The function is negative quantity x minus 2 squared times quantity x plus 3 times quantity x minus 8. And our first job is to find the x-intercept. Well, how many of these x-intercepts should there be? If we multiply this -1 times x, because this is squared, times x, we're going to get a first term of negative x to the fourth. So we should expect to see 4 x-intercepts, or 4 zeros of this function. And when we look here, we do see our first zero from the quantity x minus 2 is x equals positive 2. Now, since it's squared, it gets counted twice. It has multiplicity 2. The second solution comes from the quantity x plus 3, and that is x equals negative 3. And it is only to the first power, so it has multiplicity 1. The last solution comes from x minus 8, and that value is x equals positive 8, and it has multiplicity 1. So when we count up the multiplicity, we do see 1, 2, 3, 4. That's exactly how many x-intercepts we're expected to have, because the first one counts twice. This agrees with the fundamental theorem of algebra. Next, let's find the y-intercepts. The y-intercept is the value we will get when we plug in x equals 0 into our function. If we plug in 0 for x, we get negative quantity -2 squared times positive 3 times -8. Multiplying all that out, we do get a value of 96. So our y-intercept is 96. Then we have these last two questions. Find intervals of x where f of x is greater than 0, or we could say the function values are positive, and find intervals of x where f of x is less than 0, or we could say function values are negative. Well, here's where we're going to turn to our ideas about the graph. On this graph, I've already marked the zeros, or the x-intercepts of the function, at -3, +2, and +8. As we said earlier, our first term would be a negative x to the fourth. Now, a negative x to the fourth graph has a downward shaped U as its overall shape. So as we come up here towards -3, we should be coming up from the bottom. As we come up here towards 8, we should be coming up from the bottom. That's the bottom part of that U. As we continue this graph up from -3, we remember that the y-intercept is positive 96, so this is actually quite a ways up on the y-axis. And at some point, this graph is going to have to turn around and come back down towards that 2. Now, what happens at the 2? This graph is not going to cross through the x-axis. We said that if a 0 has even multiplicity, the graph should just kiss the x-axis. So it's going to come down here, touch the x-axis at 2, turn around and go back up. And at some point, it's going to turn around again and head back down toward that +8. And so here we've got the graph, and we can now see which function values are negative and which function values are positive. The function values are negative all the way from -infinity until we get to -3. Another section that is negative is all the way from 8 to infinity. The rest of the graph looks positive. Well, don't say positive from -3 until 8. We actually have to break this up into two sections because the graph is 0 at 2. So we say that this is positive from -3 to 2, and also from 2 to 8. And now we can go back and answer those questions about where the graph is positive and where the graph is negative. The intervals of x where f of x is greater than 0 were from -2 to 3 and from 3 to 8. The intervals of x where f of x is less than 0 were from -infinity to -2 and from 8 to infinity. The final concept for this section is a theorem called the intermediate value theorem. And it's a little bit wordy, but I'll try to explain what all this means. It says a function y equals f of x that is continuous on a closed interval a to b takes on every value between f of a and f of b. So in other words, if we have a starting function value at a, and we have an ending function value at b, and we have some y value in between those two y values, and if this function is continuous, That is, I can draw it without having to lift my pencil from the paper. Then we're guaranteed that somewhere between A and B, we will have a function value equal to that y value in between f of A and f of B. In fact, we're guaranteed all of the y values in between f of A and f of B. They're going to happen somewhere along this graph, somewhere between A and B. I like to think of this as kind of the mountain climber theorem. You can't get from the bottom of the trail to the top of the trail without crossing all of the altitudes in between. But don't read too much into this theorem. There's no part of this theorem that prevents us from having y values below f of A, and there's no part of this theorem that prevents us from having y values above f of B. All this theorem tells us is that we are guaranteed to have all the y values between f of A and f of B. How does this relate to what we've been talking about regarding the zeros of polynomials? Well, to understand, I need to tell you a little bit about my childhood. Well, to understand that, let me tell you a little story from when Mr. Grouse was a little kid. When I was little, I used to get up very, very early on Saturday morning to watch a television show. And Saturday morning, early was the only time this TV show was on. There was no recording TV back then. So I would get up early and watch Voyage to the Bottom of the Sea. Voyage to the Bottom of the Sea was this program where these adventurers, these explorers went around in this super advanced submarine and had all kinds of adventures. And as you can see from the illustration here, there was a big submarine, but there was also this little yellow submarine called the mini sub. So when just a few of the explorers wanted to go out on some kind of adventure, they could go out in the mini sub. Now, as I would be watching this program early Saturday morning, I would start to get hungry. I need to go get myself some breakfast. So I might go into the kitchen and make myself a bowl of cereal. But when I came back from making my bowl of cereal, the program had gone along. There was no pausing live TV back then. This was the olden days. And I got back, and what did I see on my screen? But that mini sub was flying up in the air. So something must have happened between the time that I went to go get my bowl of cereal and when I came back. In fact, I could say with certainty that sometime while I was gone making my bowl of cereal, that sub had crossed from underwater to up in the air. That is, it had crossed the surface of the water. And that's the way the intermediate value theorem relates to these zeros. If the sub started underwater and wound up above the water, it had to cross the surface of the ocean. Here's that conclusion written in mathematical terms. If the function y equals f of x is continuous on the closed interval a to b, and if your first function value f of a is negative and your second function value f of b is positive, well then you're guaranteed that somewhere in between the function value has to equal 0. So one of the zeros of the function must be between a and b. And of course, the same would be true if we started with a positive function value and ended with a negative function value. Somewhere in between there, the function had to cross the x-axis. Now, it may be that this function crossed the x-axis more than once. Maybe while I was out getting my bowl of cereal, the mini sub flew up into the air and then back into the water, and then up into the air and back into the water, and back up to the air. So it might have crossed the surface of the ocean many times, but guaranteed at least one time. And that's what this theorem says. Guaranteed at least one time this function had to cross the x-axis. Well, that concludes the video for this section. Now you should go out and try some problems to practice this. Thanks for watching.